Okay, hi guys. Today we will talk about a very simple NPN analog controller, which is made with basically two elements, which are the differential amplifier and the current mirror. The current mirror is used as a bias for the differential amplifier, so don't it's just used as a bias. But it is very simple to design in the most simplest way, of course. And let's check briefly the expression of the characteristic of this guy if you don't remember. You have to say that basically the current flowing here, the VC voltage is given by the product of the collector times GM VBA. That's because IC it is equal to GM times VBE, where VBE is this is the base, this is the meter, this is the base, and VB is the drop across here. This is the input in one. I don't know why this guy put it to ground. I don't really know. He was studying the impedances. But by the way, this is the IN1 and IN2. These are the two input, and the difference between the positive and the negative, we will call it VDiff. So VC1, which is the voltage here, VC2 and VC1, are given respectively by this product here, RC1 times GM plus VDiff over 2. The same for VC2. The difference, of course, will give the differential output, and you remember this characteristic, in which here it is almost the linear region. These are the common mode gain, and this is the differential gain. If you want, but if you want to demonstrate this formula, you can find it online, but it is not necessary. For this little project, it's not necessary. This guy instead is a current mirror, as you may know from a lot of courses. Just a little reminder that the reference voltage is given by this formula here. But in practice, you set the reference voltage with this resistor and with this voltage here, and the same voltage will apply in the other branch. So the basic idea of a current mirror is to use a current to voltage converter combined with a voltage to current converter. This is a voltage to current, and this is current to voltage. And so you have a current mirror. Now let's open LTSpice and let's realize this very very simple, very intuitive and simple product. So we will start by biasing everything with a voltage of 9 volts, which in most of the cases should be enough. And then we will start by putting our Darlington NPN Q1 and Q1, Q2, and also in the other branch. We want to build an analog temperature controller. So the idea is we will have the NTC here, which is stimulated by a divider. Then we have a differential stage, and then we will feed this guy to another transistor, which will do that. This transistor here will be used as a Schmitt trigger, so it will have a divider on the emitter, and then we will control the heater with some transistor which does as power control. It is a very useful project because it reminds you of all the NPN and PNP circuit as a basic, and I will use a lot of this circuit in the next video to come. So the NTC will be read here with a divider, because it is the only way to excite an NTC, and we will use the Steinhardt equation, which is R equal to R0 times the exponential times beta times the exponential of 1 over T0, 1 over 1 over temp minus 1 over T0. And Tc. Let's use the same transistor for everyone, so that we don't have any kind of mismatch or problem. Now, as I said before, we need to bias the. We need to bias. Let me cancel this and let me mirror this. Okay, so it is perfect. We need to bias the stage here, and we will do that using 2 mirror currents. Let me put just 10 kilo ohm, then I will take the equation later. We will do it by putting a mirror current here and a mirror current there. So let's do this. The first mirror current will act as a sink, current sink. So the current will flow in this way, to make it clear. And take this, and take this. Now the resistor here, for instance, 50 kilo ohms, will decide basically the current which is flowing into this. So let me connect it everything to ground. Let me choose the transistor here, and also put it to ground. And now the same to this side here, but we have to do it with a PNP, just because we have the voltage on the voltage on this side, and it is an high side. So the trick to when you have the voltage on this side here, it is better to use a PNP, because remember that in a PNP you have to provide an emitter voltage which is higher than the base voltage. This is valid for PMOS, but in a similar way also for PNP. And so we will put a PNP current mirror here. I wanted to say that there are also some other version of the current sink and current source, which is called the Widler and Wilson current. It is basically done with by adding another resistor, another transistor here, and it compensates better the base current. If you want, you can do that. I will add a beta helper if it is necessary in this branch here. So for now, let's run the simulation, just because I wanted to see how much current it is flowing in this branch. So I want to see that I wanted to see if this guy is really biased in the first place. So let me run for 1 millisecond, and let's see the current. The current here is 0.6 milliamps, and the current flowing here should be the same. It isn't. It isn't because some of the current is flowing to the base. You can skip this. You can skip this if you want. You can skip this, but you can see that the current here is. Let me put 50 volts, by the way, so that we have 1 milliamps. Okay, we have 1 milliamp, and also in this case 1 milliamp. So it is working, okay? But the collector current here is, let me check the difference between IR1 minus ICQ5, and the difference is, let me check, is 10 microamps. This can change under some load condition, okay, but we can just for let me add just a signal here, like I don't know, like 5 volts. It shouldn't, no, it doesn't change. Of course it doesn't. And the thing is, you can use a beta helper. Let me just do it. And the difference should decrease. It is not really necessary, but if you want to provide a better current, you can just do this. Now the difference should, let me put again 9 volts, and let me put 9 kilo. Now the difference should be less than before. Yes, you see that before it was 9.4, so let's try this, 9.4 microamps as a difference before. Now with the beta helper, we have 39 nanoampere. So I think that I hope that you are satisfied, but the current is working fine because it is well compensated. Okay, the current flowing here is almost the same of the current flowing here, but as you can see, it is not 1 milliamp because because there is also the drop voltage to take into account. So you either increase this voltage or you either decrease this resistor. You should decrease this resistor because having a 9.178 it is a voltage which doesn't exist. So 9 volts, and decrease this resistor a bit, 8 kilo, until you basically match 7.8 kilo, until you basically match 1 milliamp, like this. So the collector current is now 1 milliampere, and we are biasing the circuit. We are biasing this side and this side here as well with 1 milliamp. And so this current, so this BJT stage, the difference stage, it is biased with 1 milliamp. And that's what the current mirror should actually do. Now, in the other side, so let me just for a bit, because we will use a lot of blocks. So let me do this. And let me do also this. So these are 2 current mirrors. If you check on the opamp line, you will see that the differential stages are biased with current mirrors, because it is one of the best way to actually bias the circuit. Now, what we want to do is that when the temperature reaches, for instance, when T is equal to 140 degrees, we want to shut down the circuit, because otherwise our components will burn. So the best way to do this is to implement a Schmitt trigger. Imagine that I don't have any kind of op-amp, just a transistor circuit. And the best way to implement the Schmitt trigger is to use an MP, I think, is to use... so first, we have to set the threshold here, because here it is a differential amplifier. So here we'll have the temperature point. So this will set the temperature point. Yes, because here you have the NTC and here you have the temperature point. So the difference between these, so that you take the collector voltage, the difference between these two will be fed into the Schmitt trigger, which is done basically. I think that this is the most easiest way. Correct me if I'm wrong. I'm not an expert in integrated electronics, so I can be wrong. Let me put a random divider for now. I will set the temperature point later. If you put a divider on the emitter, you always have to respect the condition that the VBA voltage is higher than 0.7, And so with an emitter, you can program when this transistor will turn on. This is the basic idea of a transistor Schmitt trigger. Probably you never saw it, but I saw it on the Art of Electronics, and it works. I am quite surprised that it actually works. And so now we have to design the power stage, because it is a power heater, and it has to produce heat. But we don't want to heat so much this heater. We don't want to flow so much current in the heater. So we will have to design current protection, current limiter circuits. I swear, next time I will dedicate a video about current protection, because they are very useful. Basically, there are at least 100 circuits which does the current protection. Now we have the output stage of a Schmitt trigger like this, and here there is the voltage. So the best way here in this scenario is to implement a PNP current protection high side. The basic way to do this is just to connect the emitter here in this way, and the trick is to put a resistor here. This resistor is most of the time very low, and basically the trick is that you perform the Kirchhoff law, and you use the VBA voltage. You use the VBA voltage to provide the current limitation here. So for instance, if you have R equal to 0.7 and your VBE is equal to 0.7, basically you are saying with this configuration that you are limiting to 1 amp. Other tricks is to use the double diode series configuration with a transistor pair, to say that the base voltage here will be always the base voltage VB is always the input voltage minus 1.4 or minus 0.7 basically, and you put a resistor there. When the drop of this resistor will reach a certain threshold, which is given by this 2 diode, the current protection will be triggered, and you'll be fine. So there are a lot of circuits like this, really a lot, and they are so beautiful, in my opinion. So let's put the simplest one, which is a PNP, which is a PNP. I have to rotate this PNP. And okay, and you have to perform the Kirchhoff law in this I don't recall the the term, but you understand the concept. So we will call this limiting resistor R-lim, and we'll put it to, I don't know, 0.1. These are typical values, 0.7, 1 ohm. It depends on your project. And of course this guy has to be connected with the power supply. Wait a minute, because I risk to do a terrible job here. Okay, I don't want to short circuit this poor transistor, so we need also a pull up here, which will act as an inverter, and let's close the current limitation to this node here. Now, what about the power stage? Well, the power stage, I think that the best way is to implement a Darlington, okay? The Darlington, I want to implement, just for variety, I want to implement a PNP Darlington stage. Let's implement a PNP Darlington stage here. You have to rotate the meter to the high side towards the voltage, towards the power supply, and everything should be done accordingly. So now to cut the current protection, to make it really work, you have to imagine that the current is flowing in this branch here. So you should connect the emitter of the last transistor to the limitation current, and which in turn is connected to the base. Let me do something just like this, because it is. Let me wait for a bit, because if I'm not careful, I might screw everything at this point, because we are connecting a lot of things all together. So let me go down again. Okay, so the first transistor is connected to this base, and the second to this one, Darlington pair. Don't worry if you feel lost. I will revise everything that this circuit does at the end. And okay, now let me translate this to this. And let me bias this with 1 kilo ohm resistor. Okay. Now, since the heater will dissipate at least 50 watts, I think that we need two of this transistor in parallel. I know that this isn't the correct way to put a transistor in parallel, but imagine a design in which you have to split the power of because just one, it is not enough. And now we will connect all the emitter together. You should add emitter resistor to balance these two, but let's skip this for now. And here, as low side, we will put the heater. So let me select a different resistor, European resistor, just because this will be our heater. The heater has a resistor of like 10 ohms, and it is the best way to... Sorry, no, nothing. Okay, so now before running the simulation, now let's revise what will happen in the circuit here. So what are basically the main blocks of this circuit here? You have the NTC and the temperature point. The Darlington differential stage will compare the temperature of the NTC to the temperature point. When this will reach a certain threshold, which is decided by this divider here, it will clamp the volt, it will clamp everything, and the power stage will go down at a certain temperature point. So it is you can do the same circuit by basically using opamps with the Schmitt Trigger and whatsoever. But let me put now an equation of an NTC, which can be like 10 kilo ohm times the exponential of 100 over the temperature. Naturally, this is just demonstrative, but you should put the real equation of your NTC. This is just a demonstrative circuit, so this is just a proxy circuit, just a demonstration of how this circuit can work. This is the temperature point set, and this is the divider, which is set by this sort of Schmitt trigger. Now, if we perform a temperature simulation, we have to write .dc temp 20 degrees and 100 degrees. If we attempt to run the simulation, sorry, I just realized one fatal mistakes, and it is this. Sorry, I'm very, very sorry for this. All this part here, it is a power stage, and as such, this is a bad mistake from my side. I'm sorry. This is a power stage, okay? And as such, you will need a higher voltage and a higher current capability. So it is not correct to connect to the same voltage as the analog side. We will use, let me just say, 24 volts, so 50 volts. These are the voltages of an heater, okay? You can't, maybe even 9, but this guy will dissipate a lot. And you can even add a resistor here as a feedback if you want. It is not mandatory, but it will improve. It is not mandatory, by the way. So let's run the simulation of a DC temp, and let's see what happens. I wrote it badly, so let me write R equal to 10 kilo times exponential times 100 over 10. Okay, so let's check everything in order. This is the NTC. This is the voltage of the NTC, and as you can see, as the temperature is increasing, the voltage is decreasing. Now, this is the temperature point, which I set to 120 degrees in this example here, and when this temperature is reached, you see that the heater will turn down. So here the heater is starting to dissipate, is starting to produce heat, but when it reaches a dangerous temperature for the circuit, it will shut down. So naturally, you have to set the point accordingly. But this is just demonstrative. Okay, maybe the equation of the NTC is surely wrong. Okay, but it is just a demonstration of how an analog transistor controller can be designed. Naturally, you can do this with the transistor. It is without transistor, but with just the how can I say, with just the opamps. Let's check the limitation current. As you can see here, the current is blocked to 2.2 amps. This depends on the VBA voltage of this guy. If I increase this resistor, the limitation current will decrease as well. So now it's set to 50 milliamps. If I set it to 0.7, it should be around. Yes, it depends on the VBE of this guy. If I change the transistor, it will change a little bit. It doesn't. That's very strange. Should change, but yes, of course it depends on the transistor, but I selected the wrong one, so let me put again this guy here, and we will have the limitation current as intended. If you check the dissipation of these two, you have 5 watts. 5 watts can be really a really high power to dissipate. Okay, and so paralleling of these two can be required. Now let's come back to the VTC and to this guy here. If I increase the divider, if I decrease the divider to 6 kilo ohm, as you can see, the threshold went down, and the heater starts to turn down at almost 150 degrees. So most of you probably will say that Mano, you are stupid. You have wasted a lot of time because you could have designed the circuit with just a Schmitt Trigger and that's it. Yes, you're probably right, but I did want to do this because I revised some NPN circuit, PNP and NPN circuits, and no, I didn't waste my time because these circuits like this current limiter are very useful, and they can be combined with opamp, like I will show you in some of the next video. So as you can see, this resistor is useless. Is very useless. I think that the project is done. Okay, and I realized this with just transistor, without op-amps, and I think that it will not work probably because this transistor will probably burn. But I think that I can close the video here. Thank you guys, and let's see you in the next video.